Let's look at bond dissociation energies. This is what determines enthalpy. Like we said, the strength of bonds that had been formed or broken. So bond dissociation energy is one way that that can be measured, that can be counted up. So here's an important key. I'm going to put a star next to that. Whenever a bond is formed, energy is released. And a lot of students just try to memorize this and you end up getting it backwards, and it's never a good thing. So think of two atoms like two magnets. Okay? If you set them close enough to each other, they'll just snap right together. Okay? They'll orient themselves to their opposite poles or whatever. But two magnets, they will typically like to pull themselves together as long as you have them oriented correctly. Okay? So if you've got two very strong magnets and they pull themselves towards each other, they'll make a big crack. If it's forceful enough, you could even break two magnets doing that. I know I've broken enough magnets doing something like that, fooling around. But that sound that's made is energy that's released. It's a shock wave sent out. So when a bond between two atoms is formed, something similar happens. Energy is released. You go from unstable atoms that are unhappy on their own to forming a bond which stabilizes them, okay, makes them lower in energy and releases energy overall. So please remember that. And the opposite is true when a bond is broken. Energy has to be absorbed. Just like in order to pull two magnets apart, you have to use a good amount of your own energy. You have to apply force to pull magnets apart. Okay? So energy is absorbed. Energy is absorbed when a bond is broken. Energy is released when a bond is formed. Okay? So just think of magnets snapping together and then having to pull those magnets apart. That's a good way of thinking of it. And those energies are the same. They're equal and opposite. Whatever energy that was released when a bond is formed, that same amount of energy must be added in order to pull those atoms apart. So bond dissociation energy is just the amount of energy required to break a bond. And bond dissociation energy is a homolytic process. We're taking a bond and we are separating it equally, where one electron goes to one atom and the other goes to the other atom, making two radicals. Okay? So that's the strict energy of breaking a bond. Most of our bond breaking is heterolytic, but it actually ends up not mattering too much which way the bonds were broken. So the bond dissociation energy, it's actually dependent on the type of bond itself. Not really the molecule that bond is in, but just whether it's a CCl bond, or whether it's an HH bond, or whether it's a CC single bond, or a CC double bond, or something. Okay? Really doesn't matter at all what's in the rest of the molecule. We get a very consistent value from one atom to the next atom, okay, independent of where those are. So please don't memorize any values. I will not need you to do any calculations for this. This is just sort of reference. We may be thinking about this a little bit in the future, but just have this reference. Right? Be able to know where to look for it. There's a table in this chapter that has values of bond dissociation energies. So take a look at some of these examples here. Among the weakest bonds are those that can readily produce radicals. Remember I told you ClCl can make a radical with light. H nu, use that to show light. That'll make two chlorine radicals. In order to do that, it has to be a fairly weak bond. Strong bonds will not at all readily make radicals that way. So it requires 200, 300 or so kilojoules per mole to break a relatively weak bond. Hydrogen peroxide, that bond can break. That's what happens when hydrogen peroxide decomposes in the light. That's why peroxide bottles are brown, to keep the light out. So the OO bond is always going to be a weak bond that can readily produce radicals. That'll be important for us later. So stronger bonds, CH bonds, CC bonds, the normal bonds we have like that are going to be much stronger than these radical producing bonds. So in the 3, the 4, the 500s in kilojoules per mole. look at this trend right here. Sigma bonds become stronger the more S character they have. Okay? In CH4, the CH bond is sp3 hybridized. Okay? It is 1/4 S character. Okay? When it's sp3, 1/4 of that came from S. Okay? In ethylene, the CH bond is sp2 hybridized. That's 1/3 S. In acetylene, with the triple bond, it is sp hybridized. That's 1/2 S. Okay? The more S character these bonds have, okay, the larger percent of them that came from S, that makes for a stronger bond. Why is that? Remember, the S, when we're doing hybridization, S was a sphere in the middle. P's were those two-lobe dumbbell-shaped things. So S is closer to the nucleus. So sp3 to sp2 to sp, those are shorter bonds once we get to sp. So a shorter bond is tighter and stronger. Okay? If we go the other way, it's easier to break a bond that's longer, okay? Because the H is held a little less tightly because it's not quite as close. That electrostatic attraction is weaker the further away it gets. So that's just something that may come up again in the future. Not a huge deal right now, but file that away.